So welcome back. So I was saying that we are three groups. One group by Bekel, there's one group led by Aguer, there's another group led by Nekesa. So we'll be working together because we are going to be supervised by same supervisor, Dr. Victor and I. So we are here to guide and show you what you're supposed to do as far as your projects are concerned. So before even we start to discuss the specifics of what we'll be doing in our projects, I would like to make you understand that the work of research entirely or squarely depends on the candidate or the student. So the supervisors are there to just show you the way, but the majority of the work is to be done by you as the researcher. It's a very interesting journey, sometimes with obstacles, but with determination, you'll be able to go past the obstacles and come up with something that is very good for you and your group members, and actually, to large extent, to all of your career in academia. So a disclaimer is that all of us should be willing to work and know that Dr. Victor is also my supervisor, PhD supervisor, and is a very thorough person. He doesn't entertain jokers. So it is my wish that all of us are going to work so that any assignments given, we're able to do them and submit on time. And any work given as a group work should be done by all the group members. So the group members will not leave all the work to one person and just be available for signing. So that will not be entertained. And though as we start, our main focus in what you're going to do is to ensure that the kind of projects we are going to do can be converted into publishable work. So which means that we are supposed to be very serious with whatever we are doing so that the results we are going to get are or qualified to be published. So which means that everyone should put in a lot of efforts and be a team player. Remember, if you publish your work, then you make or you expand your academic horizon and you become different from others. So by the time you finish your undergraduate degree, if you get a publication, you are much, much far ahead of someone who has done a master's degree and they haven't done some publication. And this work should lay the ground to you so that by the time you are joining or you're coming for your master's studies, you'll have a very easy sailing when you'll be doing your projects or thesis. So for those who came in late, I'm saying that we are three groups here. One led by John Aguer, another one by Nekesa, and another one by Mark Ezekiel's group. But will all of us operate under one umbrella? The group that was created by Nekesa will be used for all of us because we'll be having the same supervisors. Today, I'll briefly introduce you to the modeling process We'll discuss the steps on what you're supposed to do as far as modeling is concerned with respect to the work at hand in producing a project that can qualify as one of the main assessment before you are actually conferred your degrees. And as I said earlier on, be serious and be a team player, because anything that comes out of this research is going to be owned by all of us. So it's upon everyone to ensure that you be a very strong team player so that all the benefits that will be accrued at the end of this exercise, you are actually able to own them, having been a very serious team player. So I'll invite some questions at the end of this presentation, but let me start by sharing my screen. Are you able to see what I'm presenting? Good. So the name of the course is SMA 480 project. So objective, so by the end of this course, we should, because it's done in group work, that's why I say we should. If it was individual, we would say I should be able to produce a project based on our mass process. So that is our main objective, to come up with a project that will be examined and award us a grade which will contribute to our overall undergraduate degree program, and it will also affect our final classification. So take it seriously. Though it's done as a group work, remember that at the end of the day, the score you get will actually affect your final grade in the course. So the other secondary objective so this we can call it primary objective. Then the second objective of this work to publish our work. So if we will be able to achieve these two objectives, then it will be a great success in our SMA 480 course. Then, so the instructors so the main one will be Dr. Juma. Then I'll also be there to help. So expectation. Every group member one, and which is very key, participate fully in the work. Then number two, be an active group member and share what you have read or learned with others. I can assure you that the research area in whichever field, there's usually no bright person and someone who is not good. All the researchers are equally important. So anything that you read and you think is as per your understanding, as far as the project is concerned, feel free to share with others. There's usually no good or bad knowledge as far as our research is concerned. What you think is out of topic sometimes it usually turns out to be the main result. So anything that you learn or you read and you think that is affecting your research in one or two areas, feel free to share with others. You'll find that at the end of the day, probably even your results, which you may think is not right, is really what is required of you. And then another general expectation is that read and reread your previous class courses, especially the ordinary differential equations and mathematical modeling, because all the things that are done as far as an applied mathematics research is concerned, revolves around knowledge on mathematical modeling, ordinary differential equations, and numerical methods or numerical analysis. We'll start by a broad area. So general structure of this project. So the first one is what we call introduction. In the introduction, we will introduce our problem. We'll introduce our statement problem. And provide the general knowledge around our research. Then two, what we call literature review. So literature review simply is the information or knowledge around the work you are doing done by other researchers. So here we provide information related to our research based on what other researchers have done. So that's what we'll put in the literature review. Like for those, in a case as SME's group, you are working on cell modeling. So here you'll provide now, you get other literatures around the modeling of the raw myosin GAF interactions, and to try to actually explain to a large extent what knowledge has been gathered so far around the concept of modeling of raw GTPSS. Then methodology. So here now we provide the models and explain their derivations. Then probably stating the assumptions used, if there are any, which obviously should be there because you can't really get a very perfect particle model. And then we have the things we do with non-dimensionalization. Stability analysis. So we have what we call bifurcations. Null lines are also here, etc. All these things are to be done. And then, so numerical simulations. So this is done to verify the analytic if any, or sometimes it's not possible to get analytical results for most mathematical models, which model the real world problems, and simply explain the dynamics of the model, etc. There's also what we call which in our case, we may not actually go there. So there's what we call model yes, confirm. So this second last procedure, sometimes for an undergraduate project, we may not go there, but as we shall grow up, probably we'll be able to do that step. So let me get the correct wording for that. There's what you call sensitivity analysis. If time allows, we may try to do them on some of the models will be right, but in most cases, due to the constant of time we have, we might not do that. Probably we might extend it after submitting the project. It's what we call sensitivity analysis. So what happens when a small change in a parameter in the model is given to the system? So how does the system behave generally? And then lastly, I will provide conclusion. Some say recommendations and conclusion. So generally, that's the structure of what we aim to be doing in this course, SMA 480. Depending on the project that you'll be doing, we may not have the whole structure the way I've written 1 to 5, but sometimes we may reorganize, especially this part of methodology, the way we organize, whether we start by, after doing the derivation of the models, working out the non-dimensionalization, the stability analysis, bifurcations, and null lines. So it will depend on the models we are discussing. probably some of the things there will not be done by those who are doing, say, a project in epidemiology and vice versa. But generally, this is the structure of how the project should look like. So the most, the way we have actually split this work is in such a way that part 1 and part 2 will majorly be done by all of you in your respective groups. And then I'll come in handy to briefly explain, help you to explain how to derive the models in the methodologies section and what we call non-dimensionalization, why we do it and how to do it. And then the numerical simulation part will majorly be done by Dr. Victor. I remember all these parts are interrelated. So you must be fully be part of every discussion for each part, because when it comes to presentation, all of you will be taking turns in presenting what you have done. Every group member will have to discuss 1 or 2 parts of all the project. So ensure that you are familiar with everything that is happening throughout the project, so that if we have to interchange any roles among you as group members, you should be comfortable to play any role on any section. So I briefly review the work you did in 3rd year on mathematical modeling, because majorly that is where we are going to derive our models, and that's where we are going to derive our problem statements. And it's good to understand how you do the formulation of the problem, because everything that we do in a project will revolve around explaining the models. So you should be able to first understand how the model is derived and how it's obtained before you start now discussing its dynamics. So if we may go back, steps of the mathematical modeling process. So 1, you have to identify the state, the most important process governing the problem. So this is what you call theoretical assumptions. And if you have done some homework, what I gave you earlier on, all the groups, you have seen that before the revision of any mathematical model, then there's always the theory behind the problem that want to be formulated. And so before you come up with a equation that explains the dynamics of the system, you need to have some underlying principles that govern the whole problem you want to model. For example, you cannot model a problem in cell biology if you don't have some basics or some theories about the cell. Similarly, you cannot do a model in epidemiology if you don't have some basics or some theory about the disease you want to model. So you need to identify the processes that govern whatever you want to model to be able now to put that into mathematical sense. Then number 2, identify the state variables. So once you understand the theory behind of what you want to model, you will now fix your state variables to explain or to take care of are the main aspects you want to model mathematically. So number 3, identify the basic principles that govern the state variables So this one, I mean, for example, physical laws or interactions. Like for those who have been studying, who will be doing a project on cell biology, the mathematical modeling of the interaction between raw GTPases and other cellular proteins, you understand that there are some underlying principles or laws that govern the interaction of those protein species. So without understanding that biology of the governing principles relating the interaction of the cellular species, you will actually not be able to come up with a viable mathematical model to explain the interaction. Then number 4, express mathematically these principles in terms of the state variables. So remember, these are a step-by-step process. So we have understood the theory, and then we understand the principles governing the interactions of the physical phenomenon of what you want to model. Then now we fix variables, which we pick just say letters. Then now, once we have that, we now bring the theory into the world of mathematics. We explain the principles mathematically using these state variables. And then the next step, verify the model. Okay, before we go to the verification, there's what you call make sure units are consistent. This will be more, make more sense when we are doing the non-dimensionalization of some systems. And then once you have the model, I remember simply a model is really a mathematical representation of the reality. So once we have the model, 1, identify and evaluate values of the parameters. Then number 2, identify type of mathematical techniques required for the analysis of the model. So that's why I told you that the structure we gave as the general structure of the a project sometimes on the methodology part, what we are going to do there will vary depending on the project you are dealing with. So the order may not necessarily be the same from one project to another project. And then number 3, conduct numerical simulations of the model. Now, when you say numerical simulation, that simply means you put the model into a computer, then with the values fixed for the parameters, you try to get different solutions by fixing different parameters and say the dynamics of the type of solutions, or how the solutions of the system behave. And then number 4, validate the model. So this means it must represent accurately the real process. Then number 5, verify the model. So it must reproduce known states of the real process. So then now the question is, how do we represent the problem? So how do we represent the problem? So problems or mathematical models can be derived or formulated differently. And we have various types of mathematical models. For instance, we have what we call the static versus dynamic mathematical models. We have what we call stochastic versus deterministic. In our case, we'll be dealing mostly deterministic. Stochastic mostly are models derived in more statistical approach or field. And then there's what we call continuous versus discrete. So if you remember what you did in mathematical modeling, so discrete models are derived or formulated using difference equations. Continuous models are derived or formulated using differential equations. And then we can have homogeneous versus detailed or non-homogeneous models. But then note, in our case, we shall use differential equations when I say differential equations, they'll either be ordinary differential equations or partial differential equations to formulate or model a problem. So we are not going to discuss all those different kinds of mathematical models on how to present a problem. So ours will be majorly, we would either give the model using ODEs or PDEs. So we are just still in the general world before we are still dealing with generality just to give an overview of the whole course before we narrow down to the nitty what is expected of us. So examples of biological problems. I'm quick to say examples and then go straight to biological problems because what we are going to deal with all the groups which are here, we are going to deal with mathematical models which are related to biology, whether it's in the disease modeling or it's in the cell modeling. So don't close your mind and think that the only mathematical models that can be formulated is in biology. I'm specific with biology because that is our main interest, but know that mathematical models can be formulated in all the fields, not just biology alone. So we have problems in ecology, and here we have predator prey systems. We have population in competition, etc. And actually, there are many interesting problems you can get in this field of ecology, especially predator-prey and this population dynamics. And then B, there's epidemiology. So this just deals with propagation of infectious diseases. So you can explain how probably a very infectious disease can actually get infected to the whole population or the dynamics that actually explains how this disease spreads from those who are infected and those who are not infected. That's in the field of epidemiology. So we have cell biology, like for those who will be doing a project on raw GTPases and interactions with other proteins. That's also the same area that I'm working on. And then we have molecular biology. We have genetics, etc. There are actually many areas or many things that can be done as far as mathematical models are concerned. So note, we need some basic skills on programming So this includes MATLAB, then we have Maple, Python, etc. to enable us perform some numerical computations. Remember, a mathematical model is a representation of a real thing. And in most cases, the equations that we use to describe reality are usually very complicated. And however good you are, you may not be able to solve the systems or the model analytically. So you'll need a computer to perform some computations. So having knowledge in MATLAB, Maple, Python, etc., and other programming languages will make the work easier. So that is all on the general introduction. So I'll go directly into a brief explanation of what we call non-dimensionalization. So the term dimensional comes from the word, the term dimension, and simply deals with the units used to describe variables and parameters used to explain or to model a mathematical, to model a problem. So non-dimensionalization is simply the process of converting the system into new parameters which have no units, or simply which are unitless, so that you make your model much easier or simpler in quotes to solve by reducing the number of parameters involved. So I'm saying making it simple or easier because the terms easier and simple are very relative. What is simple to you may be very hard to someone else, and vice versa. But the key thing of non-dimensionalization is to convert a model or a system of differential equations into new variables which are unitless, so that the new system obtained has fewer parameters than the original one, with the sole objective of making the analysis much easier. Because if you are now able to do the analysis on the non-dimensional system, and because we have one-to-one correspondence of the original system and the new system, then you will be able to solve or to understand how the original system works. So I'll explain this process using this very simple system of prey-predator interaction, what we call the Lotka-Volterra model. So consider let P be the number of prey of predators and N be the number of prey. Then we can model this situation using the system below. Remember, there are usually a million, many different types of models that can use to explain the same situation. So what I'm picking is just one of the many ways you can get a system of equations that describe the predator-prey interactions in an ecosystem. So the n dt equals to a n minus b np dp dt equals to say np minus dp, where, so you'll call this one system 1. These numbers A, B, C, and D are non-zero parameters with condition given that C is less than B. And I hope you still remember that I'm a math teacher, and we mathematics teachers, we never get old because we usually don't struggle so much when we're in class, but things which we give after the classwork sometimes are not pleasing. So being a typical math teacher as I am, I'm picking a very easy or simple model to explain the process of non-dimensionalization. And so the main essence is to help you to get the skills or the approach you can use or you can apply to your own model and then come up with a non-dimensional system. So just as a disclaimer, don't think that all the models that you are going to meet on the corridors are going to be as simple as what the teacher is giving. The teacher is here to demonstrate, and as we, the math teachers, do, we usually can't pick a very hard thing to demonstrate. We pick the simplest that everyone is comfortable with, but ensure that you have enough muscles to tackle any system that you find along the way, do the same process. So the beauty with mathematics is that the steps are usually the same. So what varies is actually the dedication and the keenness you put in it to get the correct result. So the question here, find a non-dimensional system from 1. So this is how you proceed. So we let n to be given by this. And then p to be given by this, where we let n cap and p cap are the non-dimensional variables, bar n and bar p are scaling parameters to be found. So it's a very easy process that you take the variables given, then you express them as a product of scaling parameters and what you want as your non-dimensional variables. And by the way, there's nothing special with n cap and bar n. That is just my choice. You can always pick your own notation the way you like. But remember that it will be a product of the scaling parameter and the non-dimensional parameter to define the dimensional variables you have. So for our case, the dimensional variables we have is n and p. So, which means, so where there's n, and then remember, I also need to do the same for time. So time t, you write it as bar t and say tau. So remember, bar t is a scale parameter for time, and tau is the non-dimensional time. So then it means that the n dt in the first equation will be d, where there's n you put bar n cap over d bar t tau equals to a bar n times n minus b bar n, so n cap times bar p cap. So I'm simply replacing where there's n in the original equation, you put bar n cap, where there's p, you put bar p cap, where there's t, you put bar t tau. So that's what I'm doing in equation 1. And similarly, you do the same substitutions for equation 2. So bar p cap d bar t tau equals to c bar n cap, p the same as bar p cap minus d into bar p cap. I hope you are comfortable doing that. Are we together? Good. Yeah. So once you have done that, is a normal derivative. So remember, if I give you, yeah, let's go take you back to SMA 103 class. If I give you, find what is d dt of 2x. What is d? What is a d of 2x? Or what is the derivative of 2x? Or let me say, what is the derivative of ax? With respect to what? with respect to X. You get L, correct. So remember that in my notation, bar N and bar T and bar P are just, they are called scaling parameters. So they are numbers. So when I say D of bar N, N cap is what you are calling the non-dimensional variable of N. So D of bar N cap will just give me bar N dn, and d of bar t tau will give me bar t, then d tau. This is the same as a bar n minus b bar n bar p n cap p cap. I'm just expanding the brackets on the right-hand side of question 1. Similarly, when I differentiate bar p cap, I'll get bar p, then the p cap over the derivative of bar t tau will be bar t d tau equals to c bar n bar p n cap p cap minus d bar p cap. I remember this. If I do this, I'm not losing anything. It's still the same thing. So which means then, because I'm interested having, remember the structure I need to have should be more or less the same as the original structure, where the left-hand side are derivatives and then the right-hand side are the functions, what we call the reaction kinetics. So I can remove this by multiplying bar t over bar n. Similarly, I can remove this coefficient on this equation by having bar t over bar p, so that we get the left-hand side of the first equation now becomes the n d tau So I'll have the n d tau equals to, now remember this bar t over bar n multiplies every term. So I'll have I remember this bar n cancels with this bar n. So I'll just have a bar t n minus this n and n cancels out. So I have b t, then p, n, p. Then the other one will have dp d tau So this p and p cancels out, so I'll have C by n by t n p. This p and p cancels out, so I have d tau p. So remember, the objective was, once you have make those substitutions of the products of the scaling parameters and the non-dimensional parameters, you find by n, you find by t, and you find by p in terms of systems parameter. And in our system, the parameters are these letters A, B, C, and D. So there's some interesting result here. You see this term, this part, we have A times bar T times N cap. So you find a way of making the product of the parameter A and this scaling value T to be 1. And then if you let this, then bar T becomes 1 over A. So which means that when I replace 1 over A for bar T, then the coefficient of N cap in the first equation will be given by 1. So that term, all of that first term on the right-hand side of the first equation will not have any parameter. So it's like the position which was initially held by parameter A now doesn't have a parameter. So we have reduced the number of parameters of that part. So we get the N, the tau, equals to N minus B over A NP, and then the P, the tau, equals to C over A by N then minus D over A. Do you see where I'm getting that new equation from letting bar T to be 1 over A? Are you able to recognize how I'm creating this? Good. Yeah, so anywhere there's bar T, you put 1 over A. So then now our work is even becoming much easier and simpler. So what will be the value of bar P? If you are to reason the way we have reasoned for the value of bar T, what will you fix for bar T? I remember the hint or the objective is simply to express the scaling factors in terms of the original parameters of the system. That will be the process of getting the scaling parameters. So come again, the answer. How did you get 1 over B? Why 1 over B? That's a good trial. Why 1 over B? Okay. That's okay. You are saying you don't have a reason, but you have explained what you have done. Good. Anyone else? Anyone else? B? A over B. So according to you, is A over B. Why do you think so? Correct. Remember, that's really the key thing that you do. Once you have done the fixing, it's usually a very easy process. Once you have done this fixing from step one, once you have done this kind of fixing, the objective will be now to find the values of these scaling parameters. And once you do the substitution of replacing the dimensional variables in terms of these scaling parameters and the non-dimensional parameters, when you do the simplification, if I use this problem to explain, up to this point, up to this step here, what you now start doing is to start identifying places in your system whereby one of the scaling parameters can be replaced or be substituted by in terms of the parameters used in the system, such that that part of the equation, when you multiply the scaling parameter times the parameters used, you get 1. Like what I've done here. A times bar t equals to 1. So I can comfortably express this bar t in terms of the parameter a. So t is 1 over a. So that when I put t 1 over a, t by 1 over a, then this product will give me 1. So we'll have achieved by getting the value of t. Once you have done that process, you do the replacement. Then where did my equation go? So I had this by dt equals to c over a by n, and then n p minus. So once you've done that, then the next step will be, if I am interested in getting the value of p, I just play with this part. I ask myself, if I have the parameters, or just parameter b over a times this scaling parameter, what will give me as product of those two to be 1? And you just make bar p the subject. So this would be a over b. So the person who said bar p should be replaced by a over b is actually correct. So the answer for the scaling parameter at this step, what you have done, bar p should be fixed to be a over p. And so what would be the value of bar n? So what will we fix for bar n using the same reasoning? What is a over c, correct. So remember, the value of bar n will be reasoned out from this product here, that you only have one scaling parameter here. So to be able to make the product of the parameters used in the system with this scaling parameter to be 1, you need to fix this scaling parameter to be the reciprocal of this. So n will be a over c. So by doing that, then this system becomes the n, the tau is equals to n cap. So remember, by fixing bar p by a over b, all this part will be 1. So just have minus n cap b cap, p cap. And then this other one will be dp d tau will be equals to, this will still be 1. Because now when you replace a over c by this, the product a over c times c over a will give you 1. So the coefficient of np is just 1. just have NP minus D over A times P. And you should be smiling because we have really done a great job. The original system had 4 parameters, but you see what we have here. If we let alpha to be D over A, so this now, D over A is another parameter. So I'm calling it, that ratio I'm calling it just another different letter, call it alpha. We get the N, the tau, equals N minus NP and then the P, the tau, equals to NP minus alpha P. So this is what we call the non-dimensional system. And by the way, we always have freedom. If you are not happy with this notation, once you have done all this process, for notational convenience, I can say I use simple letters. Let U be this N cap. Let the P be this P cap. And let I just use my usual time to represent the non-dimensional time. So therefore, I say, instead of writing my system in the non-dimensional form as what I have in star here, I write it as du dt is equals to u minus uv, and then the lower equation will be dv dt will be equals to uv minus alpha v, which this you can write it as u into 1 minus v, and then this other one you can write it as v into u minus alpha. Or you can say, yeah, so that's what you have. So that is what the system will be. And then you can say the du dt, I'll respond to the question in just a minute. And then this is a function of u and v. Let me check the question here. So was it a hand or a question? So yes, please unmute and ask. Why? Okay, I've just that one is just saying that u and u is common, so I factor out u. Okay, good. So remember, we are moving from dimensional, meaning having units, to non-dimensional, having no units. So when you say a system, an equation is non-dimensional or has no units, from the start, remember, I hope your question is coming from this star equation. Yeah, good. So remember from the start, we have said that the variables we are labeling with caps are n cap, p cap, and tau are what we call non-dimensional variables for n, p, and time respectively. So these are what we are using to represent non-dimensional variables for n, p, and time respectively. And the global objective of this process is to ensure that the system is non-dimensional, that every part of the system, the terms don't have units. And so when I arrive at this point here, remember A is a parameter which was obtained from the original system and it has units. Depending on the kind of problem you're solving, depending on the information given on how this model was derived, we'll be able to express the units of this parameter A. So this one has no units from our first step. So for us to claim that we need something that has no units, we need to ensure that each coefficient here also doesn't have units. And remember, A already has units, and the specific units of A will be dictated by what A represents from the formulation of the model. So because A has units, then this is a scaling parameter whose value we need to find. Then the units of this scaling parameter and the units of A should be reciprocals of each other so that they cancel out. And then at the end of the day, that coefficient of n cap will not have units. So that's why we are saying that in simple terms, to interpret how to get the value of these scaling parameters, once we have done the substitutions, we identify where the scaling parameters are, and then the product of the parameters used in the original equation and these scaling parameters should be equated to 1. And by equating to 1, in real sense, we have really divided those ratios of the two quantities to get 1. So 1 meaning that there are no units for those two, the scaling parameters and the parameter system. I don't know if that one makes sense. Good. And then another question also on the same thing. I expect you to ask another one. Just on this same stuff. You may be the same person or any other person in the audience. I expect another question. I expect another question before we delete this star, this system star. I'm expecting someone to ask me another question. Please ask. I want someone to ask me another question with respect to this star. If you don't ask, we are not going to take supper today. You must ask me from this star. Maybe I've performed some miracles here. So I expect one valid question also from staff. I'm happy that one person has identified one question and has asked. And I think from the explanation, it has gotten the sense. I want someone else to ask me another question on the same stuff. There's a time, I told you from the start that research is actually, all of us are learning from each other. And my wish is always that my students are better than myself. I want you to be better than me. I'll be very happy. If you know more than I know, I'll be very happy, especially on the things that we are going to do. Any other question? Now that we have understood how we are saying A times bar T equals to 1 and we get the value of bar T. Do you have a different opinion from start? Come on. There's one obvious question I expect someone to ask me when we arrive at star. Okay, the thing is, the route I've taken to get the value of bar T, is it unique now that we have understood how we get the scaling parameters? You have two questions. The way I've explained that bar T equals to 1 over A, is it unique? If you are to observe the structure of the system I have in star. Yeah? Okay, okay. If, what will a different person do to give bar T? If the person doesn't get 1 over A, what is another value that they can also get? And according to our reasoning, they still be right from my explanation. What else can we fix for T, bar T? Just from this step. Assuming I close from this line, if everything down, I close it. And bar T, you don't want to be 1 over A. What will be its value according to that system? One over D, okay? Is everyone able to see that? That another valid value for bar T is 1 over D. Are you able to see that? That from this point, you have a product of a scaling parameter and a parameter used in the original system. So you will still be right to say, I let my bar T to be 1 over D. This is still right. And when you do that, at the end of the day, you may get a different structure from what we have here. When you do that substitution, instead of saying let your bar T to be 1 over A, then you use let bar T be 1 over D, you will still be right. But the structure you will end up with will not look exactly the same as what we have here. Will not be the same as what I have in this box. But all of us will still be right. So one key thing that you have to be aware of, that's a very key point when it comes to these problems on non-dimensionalization. So note that non-dimensionalization is not unique. Non-dimensionalization is not unique. But you should always try to work in such a way that the non-dimensional system you obtain makes your analysis much easier. So someone probably has a question. Question? Maxwell? Why can't it be? Let me go back from my start. 1 over. Can someone respond to him why that is wrong? Correct. You can't say but t equals to 1. But you cannot express but t in terms of a parameter and another scaling parameter. Remember, the thing is that the value of bar n should be obtained, and the value of bar t should also be obtained. So you cannot express a scaling parameter in terms of the other scaling parameter and then claim that we have obtained the value of the scaling parameter. The key thing is that the scaling parameter should be expressed exclusively in terms of parameters used in the original system, not in terms of other scaling parameters. I don't know if that one makes sense. Yes, that's a good question. That's a good question. That's why I told you that typical math teachers, those are the things they do in class. It is true what you're saying. It is just lucky that our system is easier and very friendlier to everyone, and they are able to see. But the questions you are asking and what other people are asking, they make the knowledge stronger. At least from your first question, I hope you have understood that but t cannot be expressed in terms of C and N. Good. So what you are asking in the second question is right, that the system that we have is just that is very easy or is very simple. We can easily see and fish out all those possibilities of the scaling parameters. You will meet another system or systems which may not be very obvious. But the key concept that you must always remember and which will always make your work easier is that once you have done the substitutions of the scaling parameters and the non-dimensional variables into the original system, you must always find a point whereby step by step, 1 term or 2 terms of the system will allow you to express the scaling parameter in terms of the original parameters of the system. And then once you have identified that term that gives you one of the scaling parameters, you substitute that value of that scaling parameter in the whole system, then reduce it, and from one step to another step, you'll be able to get the values of other remaining scaling parameters. You do step by step. And where you may get a system of say 3, 4, 5, or 6, or n number of equations, and the same way we have just seen in this simple system, where there are 2 possibilities of how to fix your one of the scaling parameters by t, you will also realize the same, that once you have done the substitutions, you may have more than one option to choose. And at the back of your mind, remember that you do the fixing, knowing that you want to get something that is going to be easier for you to explain its dynamics. So it's just you don't want to come up with something that is even more complicated, and more complicated means it has more parameters than the original one. So you'll actually be befitting the reason as to why you are doing the non-dimensionalization process. The key objective, the main one, is to reduce the number of parameters to ease the analysis. So as we do the fixing, remember that you need to ensure that the fixing you are doing should, in most cases or in all cases, make the number of parameters in your new system to be less than the original ones. Because when you have fewer parameters, the system becomes easier to analyze than when you have more parameters. And that's why we are going through all this process of non-dimensionalization. If the system has fewer parameters, sometimes we don't need the process of non-dimensionalization, because we simply now want to make our work easy by reducing the kind of parameters we need to do. You asking another thing? No, we don't lose the information. We don't lose the information per se, because we can always retransform back. We can always retransform back the new system into original system. And that's also a very good question. Yes, the answer might still be yes or no. Yes, in the sense that if we may maybe use our current system, the original system and what we have. We are saying that initially we had 4 parameters, and now we only have 1 parameter. And this 1 parameter is in terms of which original parameters? Alpha is in terms of? Our alpha is in terms of D and A, okay? Are we together?
Yes.
Yeah. So what you're asking, you say, like for the example that we have used actually in class, it is true to what you're saying, that this process of non-dimensionalization may end up watering the original information, because what we'll be dealing with will actually not respect what we have as parameter C and parameter B. Hope you're able to see that. But yeah, so for this one, the parameter B and parameter C are actually not in use in this system. But as we shall see in the future discussion, such kind of problems whereby some of the parameters can actually get up being lost into the system should be eliminated in the process of that. You should have, that's why we say that before you start the process of formulating the mathematical model, understand the underlying principles behind the problem you want to model. So for example, this model is a predator-prey model, and relating the rates at which preys and predators actually are depending on each other. So with respect to what we have at the end of the model, it's like the B and C don't have an effect. And so our non-dimensional model will be valid if from the underlying principles, we understand that the parameters C and D has less effect on the interactions between the prey and predators. But in most cases, when you read the literature actually behind this model, you'll understand that the parameters C and B really do not have much effect on the dynamics of the interactions. But it's true, yes, that in process of non-dimensionalization, we may do some parameters. And in some cases, the parameters that can be lost may be very useful. So you try as much as possible to remember when you are doing the process of non-dimensionalization that you understand the biology or the physics of the problem, so that at the end of the day, your new non-dimensional model still recovers new parameters, which are in terms of the original parameters that really governs or affects the interactions of the system you are actually modeling. I've used a lot of words. I don't know if they get them.
Yes.
Good. So I wish to stop at that point. In the course of the week, continue reading. So remember, you are not, don't worry, even if you have not actually gotten the locus of what specifically you are going to do. That's how the research is all about. Continue reading, but before the end of the week, we will have fixed you into your respective specific zones to work in, but still to gather more information on what you're doing. You should not worry about reading. And so for the SMU Nekesas group, I hope we have given you a few basics on non-dimensionalization. So you go to Dr. Victor's thesis. I don't know which model you have actually landed on. Are you now interested in model 1 or model 2 from his thesis that you can now work on? He had given you options to pick one. Good. So this is what I can advise. Try to apply the same process to both model 1 and model 2. Try to suffer through the process of non-dimensionalization. If you get stuck, it's good. We'll still discuss, but don't get stuck in one instance and say that I can't do it. You should actually get stuck at least 10 times. Then we can come in to help. So that now you, from your own test, you see which one is easier to non-dimensionalize. And remember that the key objective of non-dimensionalization should ensure that the parameters we have in our new system are less than the parameters we have in the original system to make the analysis much easier. So for the other two groups, we will fix you before the end to know specifically what you're going to do. So one group, all of you, the other two groups, you can either decide to do projects, all of them in disease modeling, or one of you can take a project in disease modeling, then the other group can take a project in population dynamics, like what you are having this case of predator-prey interactions. So we can give you up to Friday. I still do some readings on what you have given to you and also get more other materials from internet and then see. So you either do both of you in the area of epidemiology, or one can remain in epidemiology and then the other group can work or can do project in predator-prey or population dynamics. So have a good evening. Let's keep on reading. We'll still be updating. So Nekesa, I hope all of you know Nekesa and George. So send them your numbers and let her add you to the groups, or she can share the link. Nekesa, are you in the group? Are you in? Okay. So who is going to share the link? So George, are you one of the admins? Yes, maybe you can share to them. Is it possible to share it through here? Or you have a class WhatsApp group, you can also share through them. Or you know the people here. Good. Fine. So we'll still be in touch. If you get trouble, please feel free to share. And remember, in mathematics, if you don't get trouble when you're solving a problem, then you are not a mathematician. The only way you become a serious mathematician is to get trouble. If you are solving problems and you always get answers, you are not a real mathematician. Real mathematicians should actually solve problems and get stuck and redo them up to the point they get answers. So that's really the way things are done. If you always get answers at every point you solve a problem, then you are not solving any problem. You are just picking what you can do. But real problems, you solve them and get stuck. When you get stuck is when actually the real mathematics is being done. And don't give up. The journey is very good and we'll be here to support each other. So have a good day. Good evening.